Hello, class. Okay, so I want to talk about the vector experiment. And so I have set up here something called a force table, which right now it's a bad perspective. You're looking at it sideways, and yeah, what we really want to see is this top view, which I've drawn here. But I can do a little better than that and hold up a separate table. It's a very reflective surface, as you can see. Yeah, if you look down on the table, we got this little post in the center, and then there's this like compass or the protractor, the measurements from 0 to 360 degrees. And we've got this ring with all these strings attached to it, and that goes over the center. So, and then from these strings, we can attach masses to it, which you run a mass over the pulley to minimize friction and hang a mass to it. So like here's the central ring. Well, you can see that, but there's a string that goes to this one. This is at 30 degrees. And we're hanging 200 grams from this string. And at the one at 135 degree angle, so like that marking on the circle, we're hanging 140 grams. Now, the tension in the string is a vector. So these are two vectors acting on this ring. So they're both tied to the ring. And obviously, the ring is just being supported by these strings. And so what's happening is they're pulling the ring. Like if there is no center post, they just pull the ring right off the table. But the post stops that from happening. So basically the ring is being pulled in some direction. Now the tension in the string, of course, is a vector. And so this one is obviously bigger. Let's draw it like this. Say that's the length we're going to use to represent 200 grams. This one is 140 grams, so it's going to be smaller. And so we want to add these two vectors. And we know how to do that, just from class. Graphically, we can draw a line parallel to this vector, and then through the tip here, we'll draw one parallel to the other, form a parallelogram. And our resultant vector should look something like that. I hope this is visible. It looks like there's a lot of glare on the screen. Hopefully you can see this clearly. So what we want to do is measure this resulting vector experimentally. So how do we do that? Well, what we're going to do is we're going to, like the resultant vectors here. So like these two are acting on it. And so in theory, remember the sum of these two vectors is equal to this one in like every way. So if we replaced these two forces, these two tensions, with a single string in that direction, that would be exactly equivalent to these two. And but how do we find this experimentally? We expect the net result to pull the ring in this direction. So what we're going to do is we're going to hang a string in this direction and then attach mass to it. So we're going to have these two pulling this, one pulling this way, one pulling this way. And we don't know exactly what direction the one that balances these two should be. But that's why we have trial and error. We can kind of guess it's going to be somewhere in this direction. And so we can place our string here and attach whatever weight we want to it. And if we get things just right, this ring is going to be centered. So remember, these two theoretically add up to R. I'm going to call this one A. Whatever we hang here, I'm calling it A for anti-parallel. So an anti-parallel vector is one that's parallel, like something anti-parallel to R, is in the same direction as R, but the line is parallel, but the arrow points in the opposite direction. And so we can experimentally determine this, because if we can balance the ring, then So again, this one doesn't really exist. We only have 3 strings attached to it right now. And again, when we find the one that balances it, so we have to find the angle and direction. So like if we find the right angle, angle and magnitude, how many grams we have to attach. So let's say we find the right angle, it looks like, but if there's too much mass, then it's going to pull the whole ring this way. Or if we have the right amount of mass, but say it's pointing in this direction, when it should be pointing in this direction, it's going to pull the ring this way. So we want to do this until we can center this ring and keep it balanced there by just trial and error. We kind of slide this around, add or take away weights from it, or we can adjust it in increments of grams. So in theory, we can get this to work out fairly accurately. And so once we find this A that balances the ring, then we know that A is anti-parallel to the resultant vector. Because if you just have these two pulling with the same magnitude in opposite directions, they're going to cancel each other out. So that's going to be part A of this experiment. We're going to set it up as we're told, that's given. And then we just put one somewhere in this general direction and just play around with it until we get this ring nice and balanced. And then what we get out of here is anti-parallel to the sum of these two vectors. Okay, so that's part A. And part B is basically going to be the same thing, except we want to add 3 vectors and find the result. So we're going to add like 100 grams at 60 degrees, 150 at 315, and 100 grams at 120 degrees. So we'd have 3 masses hanging, and then we'd have to set up the 4th one to balance it, just like in part A. So in part A, we're basically we're given 2, and we're just going to find like the sum of those 2 components. And in part 3, we're just adding a 3rd vector. We're adding a 3rd tension to it, and just kind of finding like the result of the sum of those 3 vectors. And that's it for this experiment. It's kind of, the idea behind it is pretty straightforward, and then just getting it to work. I do want to bring the camera over and hold it above so maybe you can get an idea of what this looks like with the, the masses hanging from it. Actually, I'm going to actually try to balance it somewhat. Now, I didn't actually set these to the right masses. We've got this mass set where you can, add and remove things, and you can adjust it that way. But just to get tension on the string so it looked right, so I didn't actually set those properly. But let me hold the camera above. I'll try to do this as smoothly as possible. So you can see right now this is not balanced. Like the ring is being pulled this way. And so if I were to add more mass, looks like that might do the trick. Or I can adjust like here, maybe it's the right amount of mass, except it's not the right angle. And if I pull it this way, again, maybe it's the right amount of mass. Let's see. So like here, it looks like it might be the right amount of mass, but still wrong direction. And so to get it to balance, looks like right about here looks good. And then, just find out how much mass needs to be placed there to keep it balanced. Because if I lower the mass, it's going to do this. Too much mass, it's going to do this. You can see it's kind of moving in a line through that center at this angle. So that's how we would go through and do this. And I can tell you this error has one very significant, the most significant error. There's kind of a definite answer as to what is the most significant error in this experiment. And I don't want to give it away, but trying to figure out what that is. I know it's hard to determine the errors involved in an experiment when you're not actually there doing it. But yeah, I guess I'll bring it up in class, see if anyone can figure out like what is the most significant error in this experiment. So yeah, this one's kind of straightforward, so I think I'll stop it here. And again, I'll post the handout that we normally give in class, and I will also post like the data, which is what you would have gotten if you were here actually doing it. So that'll be it for this one.